I would like to introduce the next speaker, Dr. David McAllen. He's a senior scientist in the Energy Geosciences Division at Lawrence Berkeley National Lab and professor of civil and environmental engineering at University of Nevada at Reno. His interests range from high-performance simulations to experimental testing on earthquake simulation shake tables. He started his career in Livermore National Lab, where he developed computational software. And I would like to welcome Dr. David McAllen.
Let's see if the clicker behaves itself a little better with me. So it's great to be here, and I really appreciate the opportunity to represent the entire EQSim team. We are doing large-scale earthquake simulations, as you'll see in a moment, if the clicker works. I think the battery is low on the clicker. There we go. Cover slide. Thanks again. I'm representing the entire EQSim team. This is an integrated team, not only from Lawrence Berkeley National Laboratory, but also Lawrence Livermore National Laboratory. And we have a team, relatively large team of engineers, computer scientists, applied mathematicians, and seismologists. This is truly a multidisciplinary problem. And I would start by noting that not very often does the venue and the location of the presentation carry such relevance to the topic at hand. And so as I get into this today, I'm here to tell you, you are sitting in the middle of our numerical laboratory. And I'm going to be talking about the Hayward Fault as our case study. Our KPP1 application for the EQSim program actually has a demonstration around the Bay Area and the Hayward Fault. So I'm going to be talking about that. But I wanted to start to talk about in a simple way the crux of our problem and why this is so challenging. And let me start with the building we're in here today. We're near the Hayward Fault. Every person in this building crossed the Hayward Fault this morning. I don't know if you know that. Arguably the most dangerous fault in the country. It runs right underneath Berkeley, runs right underneath Oakland, you know, a very, very heavily populated area, and you crossed it. And so it's really, really an important thing to understand how that particular fault affects infrastructure in the Bay Area. So let's think about the building we're in here for a moment. Suppose we wanted to understand the risk to this building. We could go over to the plant engineering here at LBL, and we could get the drawings for this building. And those would be detailed, and they would have all the dimensions. So we could construct a computer model of this building and have pretty high confidence in that model because we know everything about this building. Okay, then what do we have to do? We have to understand what future earthquake motions might occur at this site. And that's where things get very, very murky. Faults are under the ground, they're complicated. We have a terribly heterogeneous geology that those waves propagate through to get to the site. And then they interact with the building in a very, very complex way. So our uncertainty climbs tremendously when we have to understand those earthquake motions that this building is going to be subjected to. At the heart of it, the EQSim project is trying to transform the way we develop those earthquake motions and understand how they interact with the structure. And that's really the simple-minded, if you will, thought process to this. Okay, got to go this way. So how have people addressed this problem historically? Well, they've developed entirely empirical models that are based on data. We heard in the last presentation, you know, sparse data. Well, this is a really sparse data problem. And what I'm showing you here is the entire record base of major earthquakes from around the world that is contained at UC Berkeley at the Pacific Earthquake Engineering Research Center. Every single one of those dots represents a measured earthquake record somewhere in the world. If you look at that, the vertical axis is the earthquake magnitude. The horizontal axis is the distance from the site where that earthquake was measured to the fault. And you can see that matrix looks like this. If you look, you immediately see there's a lot of dots on that. There's 21,500 dots. I want you to remember that number as we go through this presentation. That's not enough dots. If you look at the yellow box, which is the region that we care most about, large earthquakes in the near field, that box is almost empty, remarkably. And so we are really talking about an empirical statistical model that is based on a starvation of data to try to develop these statistical models. That lies at the heart of why it's so difficult to predict motions with the current methods at this particular site. In addition, think about the Bay Area. I'm showing you the last set of earthquakes on the Hayward Fault. They occur about once every 150 years. Those that you work here like me happen to know we're 153 years into the next cycle, which is not good. So an earthquake is coming on the Hayward Fault. But if you look at this, the last earthquake was in 1868. That's what was in Berkeley in 1868. And today you can see, and those that you passed the Cal Memorial Stadium, the Hayward Fault goes right through Cal Memorial Stadium. So not only do we have a lack of data where we need it most in the near field, in site-specific regions like Berkeley and the Bay Area, we have no data. We've never measured a large earthquake. There was no seismic strong motion instrumentation in 1868. So that all adds up to a real challenge in terms of understanding the earthquake motions. So, what are people thinking about now? And this is really a transformational approach. People are thinking about high performance simulation to model these earthquake processes all the way from the fault rupture, propagating those seismic waves through the earth and interacting those waves with a particular structure to gain understanding. And so that's really the challenge that we're tackling. This is a hard problem. We're talking about modeling hundreds of kilometers in extent. We're talking about massively parallel grids of for example, the San Francisco Bay Area. I'm going to show you that are billions or hundreds of billions of zones, and then modeling that entire process and getting those ground motions. So, this is a hard computational regime to make. But there's light at the end of the tunnel. We are now getting access to these GPU accelerated machines that are extremely fast with very, very large memory. So like the wind project you just heard about, this is a really, really exciting time for us. We are right on the precipice, as I'll show you, of being able to simulate these processes now in reasonable compute times. And so important to this conversation is obviously the GPU accelerated systems that DOE is developing across the Office of Science. Turns out we use multiple of those. We've been using Summit for our really big runs at Oak Ridge, and I'm going to show you an example. We also are using Perlmutter here at LBL to do all of our infrastructure calculations in a very agile way. And then we're obviously very excited to get on Frontier, we hope very, very soon. The point is we're using all of these in a workflow that exploits each of those, and ESnet is sort of the glue that stitches all this together as we transfer that data from one site to the other, from Oak Ridge to LBL and back and forth. Oh, goodness. Okay, so here's what our workflow progresses like. We chunk it into three components. Component number one is the massively parallel simulation of a region in terms of the earthquake propagation. So I'm going to show you an example for the San Francisco Bay Area and the Hayward Fault. We take that data, we transfer that to LBL, and then we use that in different ways, in agile ways, to look at infrastructure. We may want to look at one particular piece of infrastructure at one location. We may want to understand the variability of response across the entire region. And we also want to be able to go in and inspect that data and look at that data to look at the realism of that data. And when you have 300 billion grid points in your surface of your domain, that's all a very, very big challenge. So let's hold our breath. If they could advance it, it'd be great. I think next slide, please, if you could. I think the battery's dead on this. So what have we been up to over the last 5 years? We have been working on the SW4 code, seismic wave propagation, fourth order in space and time, to really optimize it for this particular problem and to optimize it for GPU-based platforms. So I won't go into a lot of detail, but we are looking at very, very carefully adaptively grading our mesh so that they're matched to the geologic material properties in a vertical direction. We have pencil domains that we then propagate across the nodes on the massively parallel system. So a lot of work has gone into that. Next slide. They're having trouble as well. Yeah. So this is an example. When you're at the mall, you see the map of the mall, you are here. This is a very, very large simulation of a magnitude 7 earthquake on the Hayward Fault. In this case, the hypocenter is the star, and those seismic waves are propagating north. That's what you feel when you feel the earthquake, are those waves going underneath your feet and shaking the ground. This is a very, very large model, and it has unprecedented frequency resolution. We're resolving 10 hertz motions, very, very high frequency motions that are important to resolve for understanding the response of infrastructure. And we have about 391 billion grid points, and this was run on about 3,600 nodes of Summit. So this was a execution that we ran last fall, and we're really, for the first time, being able to resolve these ground motions at frequencies that are relevant to engineered systems. A building like this may have a natural frequency of maybe this short building of 1 to 3 to 5 hertz. We have to resolve ground motions up to 5 and 10 hertz in order to be able to actually have motions that are relevant to the response of that building. Next slide. So to give you an example of our progress, what I'm showing you here on these GPU accelerated platforms is the entire history of earthquake simulations of ground motions in the San Francisco Bay Area, going back to the year 2000. And what you see each of those colored dots is a different research group that modeled the San Francisco Bay Area. And I'm showing you the progress with EQSim in the turquoise dots on the right. Once we got on the accelerated platforms, we did the algorithm development to optimize the SW4 code. We got it running on Summit, and you can see the tremendous progress that has been made as a result of being able to utilize these new platforms. Next slide. So the other thing that we have to do is we have to, and this is where ESnet really comes in and is important, we have to be able to couple the motions from that geophysics model into our local soil structure models in a rational way, in a way that preserves the complexity of those incident and climb body waves and surface waves, so we get those effects. So we have developed and implemented a domain reduction method within our framework that allows us to go into that large database that we get from the Summit or Frontier simulation to plop our structure and soil island down wherever we want and efficiently generate the boundary motions on that local model so that we can do a substructure analysis. And this is an example of that. Next slide. So what does this translate into is our ultimate workflow, where we have our geophysics simulation on the top, and that's something we'll do at Summit and Frontier and have been doing, billions of zones, hundreds of billions of zones, 200,000 time steps, very, very large data set, as we'll see, using ESnet to translate that data over to Berkeley Lab. And then we have the flexibility, once that data set is here, the near surface data set, of doing all different manner of infrastructure simulations at will and very agile. And so ESnet is really the enabler to getting that big data set here efficiently and allowing us to operate on that in order to look at the risk in the system. Next slide. So we stitch all that together and we get to something that looks like this. I'm going to show you that earthquake again. The red dot is a location where we want to analyze this representative 40-story steel moment frame building. And you can see the seismic waves arriving at that site. And that building is now responding to that. And you're seeing the damage evolution in that building as that building yields that steel frame building. If you look at that boundary, it's working really hard, isn't it? And that substructure model that we've run here at LBL, it's working really hard because those complex incident seismic waves are very, very complicated. They're arriving at that site, and we're representing and honoring the complexity of those waves in that analysis. Next slide. So effective data management is critical. These data sets are very large, as I'll show you in a moment. So we take our geophysics model, we use the EQSim ECP developments for data. We create HDF5 data containers. We compress that data with ZFP, which is a compression algorithm, and then we translate that data either in terms of just surface motions or a near surface volume of motions that we can use in a number of ways. Next slide. So if we look at the fact that we don't know which way the Hayward fault is necessarily going to rupture ahead of time. I showed you a south to north rupture. That would be bad for Berkeley because it's directing all that energy towards Berkeley, but it could rupture north to south. So we have to look at that full suite of equally probable rupture scenarios. So that means we have to run maybe 10 or 20 different rupture scenarios of the Hayward fault to fully characterize the risk that is involved. So that generates something on the order of 3.2 petabytes of data just for the surface motions. As we move on and start to generate the volume motions, that number is going to grow. But we need to move those kinds of data very efficiently. I mentioned to you the size of the observed database when we started. That's shown in green. That's 21,540 time histories from around the world. When we do this simulation on Summit, we get 3.14 billion time histories throughout that entire domain at every 2 meters. So we have ground motions everywhere and can look at the relative motions as well as how those motions interact with the structure. So that's sort of the data challenge for us. Next slide. So we are an advocate and a user of ESnet. It really is key and enables our workflow. So on the left, we have our Summit simulations, for example. We start with 200 terabytes of data. We compress that maybe by a factor of 50 to 100 for our structural evaluations. We chunk that into 2 gigabyte segments, and we transfer that over to Perlmutter to actually do our structural simulations. Next slide. So good for ESnet. This is really great. So if we think of the data we transfer from that grid that's 120 kilometers by 80 kilometers at 2 kilometer, essentially 2 meter spacing, that results in about 3.14 billion grid points that we have to transmit data for. Every one of those grid points has a earthquake time history, a velocity time history, 2 in the horizontal direction and 1 in the vertical direction. So you do that multiplication, it's 9.42 billion grid points in that data set that we have to, time histories that we have to transfer. And so we've been testing this particular run on ESnet. We can do that in about 9 to 20 minutes, depending on our compression ratio, which is remarkable for us. Next slide. So what does this get us to? This capability, end-to-end capability, for the first time is allowing us to look at the complexity of the risk to structure in an entire region like the San Francisco Bay Area. What you're seeing here is the damage potential, where red being the hot colors and more damage, for a representative 20-story steel moment frame building at every location in that Bay Area. You see that that's very, very complicated. That doesn't look homogeneous. The complexity of the fault rupture, the complexity of the geologic path that modifies those waves, and then the complexity of the interaction between those incident seismic waves and the structure lead to a very, very complicated damage pattern. And this is exactly the kind of things that we're trying to get out of ESnet. Next slide, and EQSim. So our end game is to be able to run many realizations of a Hayward fault rupture, not one, but 10 or 20 or maybe even 30, so that we can fully characterize the potential risk at a given site anywhere in the San Francisco Bay Area. So that is really the end game of stitching all these things together. Next slide. So we are also trying a real-time example. So let's click on that URL. Hopefully it works better than the clicker. So when I started this presentation, we started the transition of those 9.42 billion time histories from Oak Ridge to here, and they're done. It took about 7 minutes and 35 seconds. The effective speed was 7.73 gigabytes per second. So go ESnet. So with that, I will end. And sorry about all the IT issues.